Hi, welcome, and thank you for joining today's webinar, Modern Particle Characterization Technique Series. This is the last of our 7-part webinar series, and we will be talking about image analysis. You can review other techniques on our website. My name is Julie Chen Nguyen, and I will be facilitating along with your speakers, Dr. Jeff Bodycomb, our product line manager from HORIBA Scientific, and Darren McHugh, our product manager from Innopharma Technology, joining us from Ireland. And without further ado, Jeff, I'm going to go ahead and pass the ball to you. When you're ready, please share your screen.
Okay, well, thank you very much, Julie. So I'm Jeff Bodycomb. I'll be taking the first half of the presentation, and then Darren will take the second half. So it's going to be a joint effort on modern particle characterization and an introduction to image analysis. A quick overview of what we'd like to do, kind of start with some introductory comments, answer the question, what is image analysis? I'm going to go through some common questions that we hear about image analysis, and then move on to how is image analysis done and some future perspectives. And it'll give us some chances to talk about various important topics as you get started in the field. Quick word from our sponsor. Have you signed up for the HORIBA newsletter? And this gets you updates and on particle analysis, as well as updates on upcoming webinars and next year's webinar series, which will be announced shortly. You can just send us email on the address on the screen or in the chat box, and we can sign you right up. And by we, I mean Julie. Moving on to some introduction, kind of orient everybody in terms of where we are in particle characterization. I have a plot. On the left is resolution of mixture components. So if you have different sizes, how well can you separate out different peaks. And across the bottom is nominal particle diameters in microns. And you see analyses going down from nanometers up to many millimeters. Digital image analysis really operates in this range at above about 1 micron and goes up to many, to millimeters. And so it really sits at the larger size of the particle characterization range. And because you're looking at particles individually, you're able to resolve out different individual components quite nicely, which is why it sits high in this graph. HORIBA, and partially with support from Innopharma, we offer range analyzers, and I have the size ranges on here. If you'd like to look at it, you can download the slides on the website and see how we go really from nanometers up to millimeters. The next analyzer down in particle characterization, so kind of looking at what else is kind of at the edges of image analysis, I would talk about is laser diffraction, which reaches from tens of nanometers up to about 3 millimeters. Now, I'll tell you, imaging is a whole lot more fun at 1 millimeter and up compared to laser diffraction. So, there's some crossover, but they're preferred operations for both sides. It's really looks by looking at scattering as a function of angle to get the size distribution. And it's very common, which is why I mention it, and it's very fast and repeatable. Some examples of results are on the left, I have silica at 30 nanometers, and I have a size distribution that we're able to measure successfully. And the right, I have coffee powder ranging from about 0.3 millimeter to 1 millimeter. So it's 300 microns and up. And tell you the truth, a lot of these measurements, you might find out you're having more fun with the image analysis. So I've said image analysis without telling you what it is, so let me fix that. Basically, the idea is that we take a picture of the particles, in our case, and then we analyze for particle size and particle shape. So on the left, I show a kind of full frame video picture, zoom in on one particle, do the calculation on it, and move on to the next particle. Well, why bother? Kind of the first answer to that, which was a little striking when I realized it, is that image analysis is often used to replace sieves, which is a fairly inexpensive technique for particle characterization, works well for large particle sizes, but hits a lot of limits. You also use image analysis to verify and supplement laser diffraction results, particularly as you're doing method development and you want an orthogonal technique. You can get to larger sizes that you can by laser diffraction. If you need shape information, for example, if you're thinking about powder flow, I might have kind of my spheres and my cubes, and they'll have exactly the same cross-sectional size, but they'll behave quite differently as you try to flow them or pack them. An example where particle size comes up is the critical quality attribute for oral solid dosages, and for the size of just about everything that goes into making your dosage form, whether it's a tablet or multi-particulate. Size relates to blend, uniformity, compressibility, dissolution rate, bioavailability, as does shape. I want to comment on replacing sieves. It's been a fairly common topic that we've encountered in our work over the years. Sieves are metal screens with holes, and well, like all screens, I guess. And you look at how many particles will pass through a screen with a particular hole size. You stack them up, and that will tell you, you weigh how much is caught on each screen to tell you the size distribution. It's fairly inexpensive to get into. Sieve sets are not horribly expensive when you first get them. But since you're beating on them with your particles, you will see that your sieves and your screen sizes tend to shift with time. So you'll just watch your results drift. The results are pretty sensitive to the operator, and there's some ways to mitigate that, but you do have to think carefully about how you shake and load a sieve, and that can lead to, or a sieve stack, and that can lead to operator variations in results. You also have a fairly small number of size classes. You can make a stack of about 10 sieves, and then things get silly. Finally, there's a fairly high operation cost because once you've put your particles on your sieves and spread it out over 10 sieves, you got to wash dishes. And so you have to clean everything up, treating the screens, particularly for the smaller, finer sieve meshes, reasonably carefully because they can get delicate. And so that contributes significantly to the measurement cost, both the time to clean and the time of measurement. A quick graph of the effective particle shape on powder flow. I pretty much ignored the impact of density with this, and I plot critical angle on the left as a function of roundness. Note here I state that 1 is perfectly round to get you oriented on what I mean by roundness, and I think Darren, when he talks about different shape factors, will comment on why you need to be careful with those statements. And glass spheres at the largest critical angle, while talc, which is the edgiest or least round, had the smallest. And so there's a real connection between your particle shape and how it flows, which can affect things like dye filling. In terms of solid dosage forms, your particle shape can affect the drug release profile. And I plot on the left percent of drug dissolved as a function of time for 2 different multi-particulate formulations. Trial A has a rough core with a sphericity of 0.87, and trial B has a smooth core with a sphericity of 0.97. And you can see there's a significant difference in dissolution for the 2 different particle shapes, even though that they're the same size. And so what's happening there is you have a dissolution across the surface, and I always interpret this graph in terms of shifts in surface area. Never went back and proved it, but there you go. So shape is important as well as size for these kinds of solid dosage forms. So kind of talk about what it is and why you might be interested. Now I'd like to answer a few questions that we get pretty often. One, how many particles do you need to measure? And then minimum and maximum particle sizes that can be measured, and the accuracy of the technique. So with image analysis, you're taking pictures of individual particles, and then you're analyzing them one by one. And you don't get that many in each individual picture, which means tend to look at fewer particles than an ensemble technique like laser diffraction. And so Everybody wants results fast. We get results faster by taking fewer pictures, but that means you get to look at fewer particles. And well, how many pictures do I need, or how many particles do I need to look at? USP 776 had one of their additions, this is around image analysis, where they gave an equation for the uncertainty U in your mean size result as a function of the standard deviation, which is the width of the size distribution, not repeatability of measurement, the number of particles measured, N, and your confidence coefficient. Often it's 2, and you can see a statistics book to get into that in a little bit more detail, but putting 2 in here is a pretty good start. So you can turn that around and find the number of particles if you know something about the width of your distribution. So for example, if I want to know my mean particle size to within 5 microns, and I know that my size distribution width is about 20 microns, and that's width is standard deviation, I can say, well, n is 20, it's actually 1.96, but 20 times 1.96 divided by 5 squared, and I say, oh, I can measure 62 particles, and away I go. So there's a nice lower limit. This equation really implies that you have a normal particle size distribution, and by normal, I mean Gaussian. You have more than about 30 particles in your measurement, or some of the statistics breakdown, and that you know the standard deviation as the width. And what I mean by standard deviation is the width of the size distribution. So here you don't know the mean, but you know the width, or you might be able to estimate it to get some numbers to put into this equation. You can also look up and find an equation to see the uncertainty in your standard deviation, which is given here, and pretty much the same assumptions. If you ever look at normal probability, these same equations pop out, and so that's why a lot of language is the same, which leads to some confusion when you're talking about the standard deviations. Well, a question becomes somewhat more practical. Does this work? What does it imply for measurement? And what we did was we measured thousands of particles and made it just a table of particle number and particle size. So you have a cumulative distribution in the upper graph in blue, that's the overall underlying material. And then we drew out 50 particles at random and did this a couple times. And you can see measurement 1 in red and measurement 2 in green. You get quite different results in size distribution. If you look at differential distribution, you can see the red and the green. They look quite choppy. They're not smooth. They kind of follow the underlying distribution, but don't do it all that well. If I go up to 400 particles drawn out at random, well, now the first and second measurements inside the computer overlay quite nicely. And if I look at differential distributions, you see that they follow the underlying distribution much better and look much smoother. So one sign that you don't have enough particles in your result is if your differential distribution is still looking very choppy and jaggy. This can also be a side effect of how you set up your bins and the differentials, but we'll leave that alone for now. So does the USP equations work? Well, for this distribution, they did. Kind of makes everybody feel good. So we kept taking out samples of 50 particles, measured the various parameters of the size distribution, and said, well, how repeatable is that? And that would be your uncertainty on the left axis. And the bottom axis is the number of particles that we kind of measured inside the computer. So the blue is the number mean size, and the black thin line is the USP calculation, and they follow each other quite nicely. And that says, okay, well, this equation works for the test sample that we had, which did happen to have a pretty close to normal distribution of particle sizes. If you decide that you want to look at the volume mean size, that's the red triangles, and you see your uncertainties increase noticeably. And if you go to look at the number and volume median sizes, your uncertainties decrease. So this equation does work for at least one sample, and certainly has worked elsewhere. But if you're not looking at number mean, you'll get in the right neighborhood, but you could see more or less variation depending on which parameters you pull out. So kind of made a take-home graph. On the left, I plot the number of particles required as a function of the width of the distribution. And I said, okay, my uncertainty, the mean, should be about 0.05. What does that line look like? That's the blue line. So if I have a width where my standard deviation or mean is about 1, I'll need about 1,000 particles, 1,500 particles. If you become interested in things like the width of your distribution, or if you're looking for a small number of oversized or undersized particles, the more details and the more heterogeneous your sample, the more particles that you need to analyze. But this graph is really the answer to that question, or at least the first answer that we give until we start making measurements. Okay, I think at this point, I am going to turn the presentation over to Darren.
Okay, thanks for that, Jeff. That was really good. It's interesting. I love the numbers part of it. It always comes back to more data is gooder.
Yeah, well, yeah, absolutely. And then it's how much is good enough.
Okay, look, thanks for that, Jeff. Yeah, so Jeff covered basically what is image analysis, covered some common questions on it. My part of the webinar is going to be a little bit more about how image analysis is done, very generic, high-level view. We'll look at some of the main steps in a typical image analysis system, not just how you acquire an image, but like how you acquire a good image and what to look out for and the pitfalls around that. We'll do some mention then, obviously, the particle size, that's the industry we're in, and shape detection using image analysis. And we'll finish up with a little bit of a future perspectives for image analysis. Okay, so on screen here, we have basically minimum size for image analysis. So what we're talking about here is your detection limits. So every method has its nuances. You know, if you're assessing particle size analysis systems, you need to be well informed. And for image analysis systems, a common question is how small can you measure? This comes down to a few factors, really. You know, like things have caught up in the last number of years, obviously with hardware and even software. And we're actually hitting the limit now of the fraction is what you can't actually overcome with image analysis. So the Rayleigh criterion, basically where the light is getting scattered when it hits the smaller particles, so their wavelength is shorter, so you can't actually detect them. So that's basically the lower limit we're coming up against. But there is other factors as well that'll affect your minimum size. So if we look at this image on the left, let's say we're just looking at a typical particle, that's getting projected onto our digital system on the right. This grid is representing pixels. And pixels are quite important because they can define the resolution of your system, among other things. So, you know, if we look at the little arrows, a single pixel here could be 0.8 of a micron. And in order for a pixel to detect an edge or a boundary, we're looking at least 50% or over half of one of these pixels being filled with the projection we see here for this system. So you can see all the orange boxes. It's quite blocky, looks a little bit like Minecraft, but that's what the system is picking up as the shape that's going to be represented in your digital system. But a little bit more on that in a moment. Okay, so then minimum size to maximum size. Maximum size is actually a bit more determined by your viewing area and the actual size that you're looking at. So if we look at this large particle and it's being projected on the virtual imaging area here, you generally try to have a rule of saying that your maximum particle size is not more than 50% of your imaging area. So say you have an image area of 11.25 by 11.25, you know, a general rule would be your maximum particle size would be 5.5 millimeters. And the reason for that is mainly because larger particles take up obviously more room. And because of that, you have more a cause and effect of them to be outside your imaging area. So you're not actually going to grab an image of those particles as much. So it's quite hard to fit them in. So that's maximum size. If we're actually talking about accuracy for image analysis systems, because we are talking about something that's taking photographs, essentially, you can use reticles or artifacts And if we look at the bottom left, we're looking at the United States Air Force resolution test from the 1950s, still used today for optical systems and vision-based systems for defining resolution. So essentially what you have here is you'll point your camera system at this, you'll look at the bars and lines that are getting progressively smaller and smaller, and your image system will have a point where it can't see a gap between these lines anymore. The lines will become blurred, and that's your level of resolution, among other things. The great thing about these reticles and artifacts is they're all traceable. They all comply with either ISO systems here in Europe, or ASTM systems, or NIST systems. So they're all traceable back to original standards. So basically what you're seeing is what you're getting. So if you're measuring this and it's measuring correctly, you can say that it's traceable back to the original size. So a little bit about how image analysis is done. Essentially what you're doing with image analysis is you're augmenting an original image by either using either filters or thresholding to obtain information that you want. So there's huge flexibility here. This is probably one of the reasons why image analysis is so popular. You can do a lot with a digital image. So even if you think of even filters that we use in everyday life, maybe some social media filters, it's much the same, only on an industrial application, but we're not going to be putting bunny ears on a particle anytime soon. But it is essentially what's happening in the back end. If we look at the main steps in a generic image analysis system, what you have is your acquisition, your hardware, your camera system grabbing that image. It's going to visualize it for you. We step down into the digitization of that. So we're going from analog to digital. That's getting converted over in the camera. Typically, a thresholding step is applied here automatically to convert it into something a bit more viewable. You might be binarizing the image, taking it from a color image to black and white. And then the next step is image processing. And a lot can happen in this one step of image processing. So if we look at the images on the left, we have a Icon 2 image up on the top left of some particles, and you can apply a plethora of filters using any type of image analysis software. We can do edge detection, we can do grayscale, binarize, black and white, or we can single out different masks in different areas of that image. So there's a lot of processing that you can do with it, depending on what your interest is, depending on what the feature is that you're looking for. And that's, for us, is going to be obviously particle size and shape. So from that, once you grab your feature of interest, that can convert it over into data. You've pulled out the ones and zeros that you're interested in, and that's where you build your statistical analysis. And for us, that's going to be PSD, particle size distribution. A little look at, I guess, the hardware setup. Again, if we take it from a kind of generic point of view, you're going to have your image acquisition, which is your hardware, which is your camera setup. Looking at your material, you illuminate the material, the light reflects off it, bounces back to your camera lens, that gets picked up on a CCD or a CMOS sensor. If we look at this image digitizing step, we can see that we're illuminating material, light gets reflected back to the imaging system. This is where we're going from analog to digital, and that gets converted over to a digitized plane, much like the pixels we've seen before. From that digitized image, then it goes to image processing, and that's where you can do all your analysis or all your editing to your image. Okay, so just to talk a little bit about common image capturing methods. So there's basically two methods on the market, and that's static image analysis and dynamic image analysis. Both covered by ISO standards, 133221 and 133222. Okay, I got those numbers correct. Basically, one is where particles are measured stationary, and the other is particles measured where they are flowing or moving. And I'll let you guess which one is static and dynamic. But there is benefits to both. Static image analysis can sometimes achieve a little bit of a higher resolution, a little bit of a higher pixel size. So you can go sometimes a little lower on those lower size limits with a static image analysis. But then, of course, it also has its drawbacks. Your material static. It's typically used as an outline setup, so you can only measure a finite amount of material. Whereas dynamic image analysis has a benefit of being able to be integrated inline, so you can measure it in a process or flow more material by it, increasing your stats really. So acquiring images. Yeah, this is quite possibly one of the most important steps I feel of image analysis is actually your image before you break it down. And what dictates your acquiring images is your hardware, and that is going to be your illumination and focus. So we can see on the left here, we have a particle. You know, by the human eye, we can recognize that that's a particle. It's a little blurry. It's not very well illuminated, but we could still tell it's a particle. Well, unfortunately, because it's a little blurry, the edges are a little less defined, meaning more pixels will probably be spread out on that, and we're not going to get as tight a edge detection when it comes to our image processing. On the right, we have a nice sharp image that's been well illuminated and focused on at the right plane. And that will aid us when it comes to image processing. So I guess the coin and old phrase, garbage in, garbage out. You have to start with good images. So it really is about the hardware setup at first, getting the correct illumination and focus for your material. And then from there, at least your image analysis, your processing, at least that's all editable and configurable. Yeah, so if we talk a little bit about dispersing samples, that can be consideration for particle size analysis. You'll often want to spread the material out. Let's say if we're looking at a binary image here, like a black and white image on the left, and the materials are touching, it can make it a little bit more difficult for image processing to define those edges. So you might have to either put the image through some more filters and steps. Watershed is a good tool for actually separating joining particles. Or you could actually look into mechanically dispersing them. So you can use an air jet, or it could be fluidized, or you can use gravity, and the material will actually naturally fall past the camera system separated. And that just aids your image analysis. It's one less processing step and room for error. So we talk about the analog to digital journey. And if we talk about, I guess, color images, I'll just put these next two slides up. So we have a icon 2 image on the left of a cellet, and if we zoom in on that a little bit, you can even see the little bit of pixelation from that being zoomed in. So we're talking about that image being captured by a camera system, goes to your CCD or CMOS sensor, it gets digitized. This is a bit of a overzealous interpretation of pixels, but you get the idea of where the edge of the particle is depending on the color. The background is a lot darker. And what that will do then, it can get converted to pixel quantization. Basically, it gets converted to ones and zeros. And for a color image, that can range from, I believe, from 0 to 255. So that's how a color image can go from analog to digital. If we look at segmentation, so before, actually for the dispersion example, we've seen some particles touching. If we're looking at, again, a binary image here, just two-tone, and the particles are touching, our image analysis system on the left might detect this particle as one because there is no defined boundary between the two of them. So this is where you would want to come along with some of your filters. Again, Watershed was a good one for separating particles like this I've seen in the past. And then you can define two particles. So you can do a lot of good processing for segmentation with your image analysis. Again, the flexibility is there to do that. One of the things of the icon system, because it's a color image, you can detect overlapping particles versus binary images, where black and white might not show this as well. So we've zoomed in again on two satellites here, one sitting on top of the other. Let's say we digitize this, we break it into its pixels, and because there's different thresholds and color changes going from one particle to the other because of the crossover of light, we're able to define a better contour or a better edge on that particle. And then another step as well is the amplitudes can be detected, and if more than, much like the pixel, if more than 50% of the particle is visible underneath another particle, we can project the contour around and get an edge detection on that. So if we move a little bit on from, I guess, some of the fundamentals of image analysis itself and the filters and such you can use for that, and we bring it back a little bit to our industry and particle size. Jeff alluded to it before, but there's more than one method. So if we take an image on the left here, this is, I believe, from the PSA 300. There's more than one way to decide on or choose your particle size. So XC min, which is like a minimum chord width of a projected particle, is what we're looking at here. This is very useful for actually comparing to sieve analysis. So sieve analysis, as traditional method, most used particle size determination method in the world, but it does have its drawbacks. You could imagine this long particle can actually fall through a sieve, so it'll be classified as a certain size of falling through a mesh, but it's actually much longer than what you're seeing. So XE min, taking the shortest chord length, is typically very comparable to sieves. X area, which is the diameter over the projected surface. What we have here is a equivalent area of the granule above it. The circle is the same area as that black granular shape. Then we also have length, which could be, let's see, XF max, and that's the maximum chord length. And then also you can take the major and minor diameters, major and minor axes, and project an ellipse around that, much like the icon system. So I'm mentioning here that this is well suited to sieve, and shape parameters can also be calculated as well. And we'll move on to that. And that's one of the benefits of an image analysis system, that you can actually determine shape compared to some other particle sizing technologies. So if we go into particle shape, it's actually much the same. There's more than one calculation to determine your shape. So if you are comparing particle size systems, you're doing orthogonal techniques, always make sure you're, I guess, comparing apples to apples. And if not, you're looking for more of a correlation than an actual direct comparison. Because even for aspect ratio, one of the probably most widely accepted shape methods, there's actually more than 3 ways you can define aspect ratio, as seen on the left here. So you can get 3 different numbers with that. Another method for particle shape is eccentricity, which the icon system uses, and that goes from a measurement of 0 to 1. So 0 being considered a perfect circle, 1 being a straight line, and you'll never get a measurement of 0 because, well, nothing's perfect, and you'll never get a measurement of 1 because nothing's ever truly straight. So we have the formula there for how you measure eccentricity. That's another method of doing it. But also there's a lot more methods out there as well for determining shape. So depending on your background or your process, you can decide on what's suitable there for your material. Okay, so that's kind of wrapping up my little bit about image analysis and what it is and how you do it. For image analysis systems, we have the PSA 300 here by HORIBA. And then we also have the Icon 2 by Innopharma Technology. There are 2 product offerings that fit the image analysis bill. And then I just wanted to finish a little bit up with where we think image analysis is going now. And it's probably already there, to be honest. But it's just to highlight a few little things around how IA is going AI. So image analysis is becoming artificial intelligence, the big buzzword at the moment. So I want to talk a little bit around this just for a minute or two. These slides are borrowed, or I should say stolen, from our head of software. So I'll be talking more of a high-level view of what machine learning is and how it can have an effect on our image analysis and subsequently our particle size analysis. So yeah, the buzzword at the moment is artificial intelligence, and what that can break down to is machine learning, which is under the umbrella or of that. So basically, you have a machine represented by a little robot here. You feed him information such as this is what a dog looks like, this is what a cat looks like, and so be it. And then when it goes and views them in the real world, it can actually make predictions. So if it sees a dog, it'll predict that it's a dog. If it sees something that looks like the cat, it can have a confidence interval that it's 90% sure that this is looking at a cat. Or it can also have slight confusion of things that look the same. So we're looking at a bird here, but it's coming out of the chicken. Or we can see something such as an elephant and not represent it at all. So that's some of the benefits of using machine learning. You can train basically a model to pick out information that you're interested in. Much the same way with image analysis, we're interested in pulling out features from digitized data. Machine learning can do the same. So if we look at supervised machine learning, a classification within it, you can feed labeled data. So let's say example of you have 1,000 images of particles. You train 500 of them. And when I say train, you manually annotate what the particle size is inside those images. click and drag and drop circles and say, yep, so this size. You feed that to the machine learning algorithm. You take the next 500 set that are unclassified and use that as your test set to see how well you did. And then it's an iterative process as well. Okay. The other model, which is a bit more black box, is unsupervised machine learning, which is where you probably go into more of the big data terminology. You might have to take 10,000 images, feed that into your machine learning algorithm, whatever model that's using, k nearest neighbors, random forest, etc., even neural networks, and see what it outputs and see what it determines are the features of interest from that. So unsupervised machine learning can have greater benefits if your data set is larger, but because it's a little bit more of a black box in terms of how it comes to its predictions, it's been viewed a little bit with caution, I guess, especially from a standards point. Where supervised machine learning is starting to take a lot of adoption in ISO, and there's even been mentions of it in some FDA regulations as well. If we go a little deeper than that and we just talk about neural networks and a type of machine learning method, so we can take images. We see these images on the left of 3 different types of particles. You can label those using whatever method you have. You can put them with different weights into a neural network, and a neural network is supposed to be thought like the human brain, where you have synapses. Different chemicals will fire different reactions, and they'll all feed back to each other, thousands of times per second, and until the correct answer moves to the next hidden layer. So you can have multiple of hidden layers inside a neural network. The reason this is also becoming, into fruition as well, there's been huge advancements in computational technology. The overheads for producing these types of networks has come down drastically. So so you can backpropagate what the information is based on the weights, and the error between the output value and the expected value can be determined. So I just wanted to finish off with that, really saying that I think image analysis is turning into artificial intelligence, but it's probably not as easy as we think. There's ways to go yet. But there is, there's lots of development in this area. So, things will be coming soon to the market regarding particle size and artificial intelligence. We already see artificial intelligence pretty much in our everyday lives with, autonomous vehicles, facial recognition, all these good things. And it's going to start becoming, getting into the user hands more and more. So image analysis is definitely going to be going more toward machine learning, where the end user can actually build their own algorithms for particle size detection, giving it a more tailored look. Okay, that's it from me.
Well, thank you so much, Darren and Jeff, for the excellent webinar. I was still processing how it would be like for the AI as we move forward towards that direction. Yeah, I can only imagine how much time we would save from babysitting these analyses. So that said, a few questions that came in, and here, let me start with one, and feel free to take on any of these, Jeff and Darren. Question 1, how to decrease the noise caused by low resolution images or untidy experiments?
So I heard low resolution. What was the second noise source?
Low resolution images or untidy experiments.
Oh, untidy. Okay. Yeah, I think they're two separate things. So low resolution images. Depending on your options, you can do some improvements, as in smoothing with your image processing, but that again it has its limits. I think it kind of goes back to that step of focus and illumination. You got to be trying to make sure you got the most sharp, well illuminated images to begin with, rather than trying to Photoshop them later. The second question, what was that again, Julie?
How to decrease the noise caused by low resolution or untidy experiments.
Yeah, well, untidy experiments, improve your experiments.
Well, one thing you'll notice, particularly, is that if you have some very fine particles that just came dust from the air and don't belong in your sample, you can tell your image analysis system just ignore everything under 2 microns. And it's fairly common to ignore stuff that's a single pixel size on your camera because that suppresses camera noise anyway. So you can help yourself with a little bit if with setting rules for what you accept as a relevant particle. Now, of course, if you set that rule, that means that if there are any 2 micron particles that work their way into your sample, you'll never see them. And a comment on rules really goes back to what Darren mentioned earlier. If you clean up your experiments, and the less you have to rely on rules, generally the better results you have. But if you have to save a measurement or save a result, kind of rescue something, then you start saying, everything that looks like dirt, so dirt's generally under 2 microns, I'm going to ignore things under 2 microns or things that are over 100 microns or stuff like that.
Sounds good. Thank you. The next question, what is the resolution of these techniques?
So if you want to hang numbers on it, the resolution, say, on the PSA 300 is, well, I mean, now we're down at the Rayleigh limit, so about half a micron. Now, going back to kind of Darren's comments, I have a half micron resolution, but if you hand me a 2 millimeter particle, that system won't get that resolution in any useful way because of the field of view. And so your resolution is going to become coarser as your particle sizes get larger, just because of the trade-off between pixel size and field of view. Yeah, I don't remember the icons offhand, but it's
yeah, it's a little larger. So our pixel size is 5.5 microns. So our resolution is like 11 microns. But it's the same thing. If you put a 11 micron particle in front of it in perfect conditions, you'll measure it. But the repeatability of that is very hard. So hence we say the lower limit is 50.
Yeah, and then so with the icon you go up to a larger pixels, 5.5 microns, but you get to look at much larger particles because the upper limit is several millimeters, which is high. We have much higher upper limit than the PSA 300. So yeah, even that depends which analyzer you have.
Well, it gives me a great opportunity to share with you then. We will follow up with you on this question specifically. You can also send us questions at labinfo@horiba.com. This question came in. So in industries where particle sizes are quantified by sieve screen sizes, will this report by comparable mesh?
So I guess I'm going to put that over to you, Darren. I know the PSA 300 does not report as mesh sizes. I could probably beat it into submission.
Yeah, so, similar as no, it exports the full particle size distribution, ranging from D5 up to D95. What you can do from that data then is either build a macro or your own Excel table just to convert that over to equivalent mesh sizes, which we have built before for people in the past. But internally in the software itself, it just outputs what the full particle size distribution rather than equivalent mesh.
So what is the expected sample analysis time then for icon 2? And I might as well answer for PSA 300 as well.
Sure, I'll go first. For the icon, it's on average 5 seconds. And we say on average because it depends on how many particles are in your image. If it's a very packed image, it can just take a little bit more computational time to do the full analysis of that image. So it could take 6 seconds, but if it's not a fully packed image, it could be as quick as 3 seconds. So on average, it's 5 seconds. You're getting updated information about the particles.
And so the PSA 300 is about the same, a few seconds per image. 5 seconds sounds like a reasonable number. Kind of one thing that's between the two, Julie, well, I guess you're aware of this, is that the icon is often put into a manufacturing process, and then the particles are just automatically refreshed in front of the device for updated, for a fresh set of particles for more statistics, whereas the PSA 300, we move a slide around. And then as for the duration of the measurement, that goes back to that question of how many particles do you need to measure.
Thank you. So hopefully that was satisfactory for our audience. The next question goes back to the resolution. What is the resolution at 2 millimeter and at 50 micron?
Yeah, I'll have to come back to that one. I'll have to put up.
That's okay.
Yeah,
Absolutely.
yeah.
We'll definitely
Me too.
follow up with
We
you.
have to go look at our tables.
Yeah.
Okay. So the next question is, I can probably combine these two into one. How to confirm the actual size of non-spherical nanoparticles? So I think that comes back to what's the size range for PSA 300, since we're looking at nanoparticles and nanowires.
Yeah. Yeah. So I guess, so if you have a nanoparticle that is less than a micron, then both of us have pretty much been talking about optical microscopy. If you need a measurement, an image type measurement of that, and this certainly has been done, is you would move over to electron microscopy or some sort of scanning, tunneling microscopy. So if you have such small particles, you would have to do that. Nanowires are a little bit funny in that even if they're very, very thin, sometimes you get an image if they're long enough. You're not going to get a great image, but you're going to get some kind of rough shadow to say how long they are. But you won't be able to talk about, much about diameter. And so, yeah, and if you're at nanoparticle range, you're really looking at the scattering techniques for routine analysis. You're looking at nanoparticle tracking, dynamic light scattering, and laser diffraction.
Thank you, Jeff. Okay, the next question, I can probably address that. For typical equipment costs, we will reach out to you
Yes.
offline. For the next question, and I see that this might be the last question, what caused D10 values to change when analyzing the same sample in replication? So in another word, I guess the D10 changes when this person is doing repeatability analysis.
Okay. Could be a few things.
Go ahead, Darren.
Yeah, sure. No, could be a few things. So like your D10, you're talking about your smaller size, your particle size distribution. Typically called the fines. If you're doing a repeat test and they're dropping, it could be, I don't know what's happening in between, but it could be attrition. You could be getting small breakdown in the material, and hence the generation of larger or more fines. I mean, not larger. But I guess it's hard to know without knowing more about the process. But yeah, typically that's what we'd attribute a drop in your D10 versus your D50 and your D90. If they're staying steady and your D10 is dropping, it's the first signs that you're getting breakage, you're getting material breaking down.
Yep, I kind of agree with that.
Okay, that's all the questions that we have now. Again, please don't hesitate to reach out to us if you can think of other questions or feedback that you may have to labinfo@horiba.com. I think that's about it. Do you have anything else that you'd like to add, Jeff and Darren, before we wrap up?
I'm good.
No, thank you, everyone.
Perfect.
Yes, thank you
thank
very
you so much. And we'll see you at our next webinar in 2021.
Yes.
Thank you.
Bye.